Swayam Prabha. Digital India. Educated India.
Hello, welcome to this course on astrochemistry. I'm Raghunath from IIT Tirupati. So, the word astrochemistry, when you look at this word astrochemistry, it consists of two parts. Astro, which roughly translates as something about space. And chemistry, I'm just writing it as chem, is the study of atoms and molecules. You actually don't require a course to tell these two things, right? But taken together, astrochemistry, therefore, it's very easy for you to understand that astrochemistry probably is going to be the study of atoms and molecules in space. So that is what this course is going to be all about. Now, before we proceed further, we shall look into who is this course going to be useful for. Now, if you're a chemistry major in college with some background of college chemistry, you should be able to understand this course. If you're a physics major, you must have studied definitely about astronomy and astrophysics. This course on astrochemistry shall be complementing you very well with your knowledge of physics, and the only requirement is high school level chemistry knowledge or perhaps some ancillary physics knowledge. And lastly, if you're an engineer who is interested in more about space sciences, the various aspects of science connected with space, you would also find it useful. So the target audience roughly is let's say some third-year BSc students of like both chemistry and physics majors. You can also be a first-year MSc. It's never too late. First-year MSc, or if you're a B or BTech student, right? You may also find it interesting if you want to study more about fundamental space science. And lastly, I forgot to add this point. Even if you happen to be a PhD student in astrophysics and you want to understand at the molecular level what's happening in space, you may also be finding this course useful. So this is the intended audience for this course of astrochemistry. The next point we shall be looking into is, so let's now dissect both these phases, astro and chemistry, a little bit more. Now, the moment I use the word astro connected with science, what other phrases come following astro? What do you think about naturally? Immediately, yes, you think about astronomy and astrophysics. You're very right. And what does astronomy entail? Astronomy entails, calculating the relative motion of molecules, calculating the relative motion of celestial bodies with respect to one another, finding their positions, and also observing them using a telescope. That is astronomy. And this has been going on since ages. If you think about it, astronomy is a very old science. It is said that the Greeks have studied it, the Babylonians have studied it, the ancient Indians have studied it, the Egyptians have studied it, civilizations which no longer exist, such as, for example, the Hittite civilizations, people from those civilizations have also been studying astronomy. So, astronomy is a very age old subject, which was, of course, nonetheless augmented ever since, the modern telescope was invented. When I say modern, I'm talking about approximately in the 1600s. With the advent of the telescope, the science of astronomy got more and more accurate. So it's all about measuring, you can say, the position and dynamics of celestial bodies. What are celestial bodies? Whatever, you look above and then you find beyond the atmosphere of Earth. They're all celestial bodies. Now, what is astrophysics? This is much more interesting. This is applying the ideas of physics, classical mechanics, thermodynamics, quantum mechanics, and statistical mechanics to space sciences. Now, it is said that the advent of astrophysics came somewhere approximately in the 1860s. Now, with Fraunhofer, Fraunhofer, the German scientist, observing the sun spectrum. Now, Fraunhofer was an amazing experimental scientist. He combined the use of a telescope along with, a prism and some a diffracting slit, and he was able to get an amazing spectrum of the sun. And he recorded that whatever was observed in the spectrum of the sun was later found by some other scientists to match with what is found on Earth. Now, this marks a very, very important epochal beginning in astrophysics. It tells us that the sun, while it is very far away, is also composed of elements and atoms which are present on Earth. So, this way, astrophysics, which took birth in approximately the 1860s, has since progressed, encompassing several areas and igniting several young minds. You have the programs such as ISRO and NASA, the European Space Agency, etc., etc. All of them actively promoting astrophysics, and it's a very exciting area of science. Now, it may have intuitively occurred to you to think about astronomy and astrophysics. However, astrochemistry is not something that you think about very intuitively. In fact, if you ask the more recent Gen Z students, as they're called, they'll also tell, "Sir, I'm also interested in astrobiology." Wow, what is this astrobiology? Now, if astrophysics roughly deals with the formation of, let's say, stars, galaxies, etc., etc., astrobiology roughly deals with the formation or the origin of life in the universe. So, I mean, if you can understand this, I've written right over here, astrobiology refers to the formation or origin of life in universe. Okay, so astrophysics concerns itself with formation of stars, galaxies, and astrobiology concerns itself with the formation or origin of life in universe. Now, what could connect both? On the one hand, you talk about life forms, and on the other, you talk about the places where life can exist. What connects both? As it turns out, the science of astrochemistry, it connects astrobiology with astrophysics. How does it do it? Well, this studies life, and this studies, the places where life can originate. I mean, I'm using the phrase place very loosely here. And it is through molecules. That you connect the concept of life itself with the places where they originate. So therefore, it would definitely not be an exaggeration to state that astrochemistry is a central science connecting astrophysics with astrobiology and whatnot. Okay, so on this note, we shall study further about astrochemistry. Now, before we proceed further, I want to bring to your attention the latest feat of ISRO's Chandrayaan. Let's call it a small So before we actually proceed along the lines of studying more astrochemistry, here's a very important detour. Now, let us think about what ISRO did recently. What happened recently? Approximately some 2 months ago, Chandrayaan 3 was launched, right? Do you all know the objectives of Chandrayaan 3? What were the three objectives of Chandrayaan? The objectives of Chandrayaan were A, to demonstrate smooth landing of the lander on moon. This was one objective. Another objective was to showcase the ability of the rover to navigate, to move along, to move on moon. This was the second objective. And the third objective, is very interesting. The third objective is to collect and observe details regarding the composition of moon. Now, if you consider all these three objectives, what does this involve? Right? To demonstrate the smooth landing, you have to use a lot of physics principles along with engineering principles. So this is the astrophysical objective of Chandrayaan 3. What about this one? It's also similar, right? You're considering the motion of a rover, and the rover follows Newtonian mechanics. And so this is also concerning itself with astrophysics principles in conjunction with lots and lots of engineering details. What about this person? To collect and observe details regarding the composition of the moon. Now, this involves, of course, a lot of engineering principles and physics principles also, but there are some chemical ideas involved. And this objective highlights the need for astrochemistry, the need to understand astrochemistry, and why it is very important to study about how molecules behave in space. Now, you may ask me this question, okay, but why do we care about molecules in space? I understand that we are sending some lander, we are sending some people over to moon. I understand all of that. But why should I ever be concerned with the composition of the moon, or like what molecules exist in space and how they behave? I shall answer this question by giving you some examples. The first example I want to highlight to you is, now here is a mix of chemistry, physics students and some engineering students who have taken some basic science, correct? Now, you must have all heard about redox reaction, haven't we? Now, what are these redox reactions? It's a combination of reduction and oxidation reactions happening. What is reduction? Reduction is some for example, let's say this is a gas phase reaction. Now this is a reduction reaction, which is a gain of electron. Now, au contrary, I can also imagine This is a loss of electron. And this is an oxidation. Now taken together, right? Now taken together, we get what is called as a redox reaction. It's a combination of reduction and oxidation reactions, which is you just add these two reactions, the electrons get cancelled out, and it becomes x plus y minus, giving x plus y. We're not worried about what phases these reactions happen in. Now, the point I want to convey to you is that on Earth, or let's say, have you ever seen a reduction reaction happening in isolation in the absence of an oxidation reaction? Is my question clear? The question I'm asking you is, we all understand that redox reactions happen. We have been studying them. We have been studying a lot about how to balance them in a lot of high school chemistry, as well as in some undergraduate chemistry. But do we ever see a reduction reaction happening in isolation in the absence of an oxidation reaction, or an oxidation reaction happening in the without the occurrence of a reduction reaction? The answer is no, not on Earth. Because these electrons are high energy species. Because these electrons are high energy species, whatever electron you get whatever electron you use has to come back, such that in the overall reaction, the electrons get cancelled out and only the chemical species remain. So because the electrons are high energy species, they get absorbed onto some atom or molecule somehow, right? We do not see any reduction reaction happening in isolation or an oxidation reaction happening in isolation. This is a very important point to note. However, in space, I'm not specifying which part of space, we shall look into this as we progress along the lectures. However, in space, a reduction reaction or an oxidation reaction could take place in isolation. This is a very, very important point. I want you guys to understand it. Let's take the example of, there's a lot of hydrogen in space. Lots and lots of hydrogen in space. Now, just like on Earth, we have electromagnetic radiation surrounding us. In space, there are some high energy waves called as cosmic rays. Now, these cosmic rays supply enough energy that they knock away an electron from H2 to give H2 plus electron. Now, what is this? This is an oxidation reaction. And notice that this happens in isolation. This is not accompanied with any other concomitant reduction. Why does it happen? Because the cosmic energy rays are so high in energy that the electrons, which are high in energy on Earth, appear to be much lesser in energy than the cosmic rays. So therefore, this reaction can proceed in the forward direction. Isn't it fascinating? What we understand from this example is that what the chemistry not happening on Earth can happen very readily in space. And why does it happen? It happens because the electron, which is supposed to be a high energy species on Earth, right, is much lesser in energy in comparison with the cosmic rays. So therefore, right, an electron can easily get knocked off. And because these, what are understood to be higher energy species on Earth, because they can exist as such, you don't need any other molecular atom to absorb the electron. Therefore, an oxidation reaction or a reduction reaction can happen in isolation. For any chemistry student or a physics student who has studied chemistry with some depth, this is a shocking news, correct? Because in your high school or college, if you write only one half of the redox reaction, either the reduction or the oxidation part, you won't be given marks. You'll always be asked to write the complete reaction. But hey, here in space, the complete reaction is the one half itself. So therefore, we learned from this example that we can learn a lot more about chemistry, the fundamental aspects of chemistry, by probing the behavior of molecules in space. This was one example. Let me, take another example. Let's say, we consider so if we consider acid-base chemistry on Earth, what do we know? Say, for example, we take this generic example of some acid HA and some base B minus, right? And we typically study acid-base reactions on Earth in water. That's the textbook example, right? Let's consider this reaction happening in water. And how do we understand acid-base chemistry? Well, we understand that this base abstracts a proton to form the conjugate anion of this acid HA. So we get BH and A minus, correct? Now this is base 1 and this is acid 1. This is going to be my acid 2 and this is my base 2, correct? And acid 1 and base 2. Base 2. Similarly, base 1 and acid 2 are what are called as conjugate pairs. Correct? So this is the understanding of acid-base chemistry happening on Earth, from a high school level or even first year college level, correct? A base abstracts a proton and then we get another acid and another base, right? Now, this also is to be understood as happening in water being the solvent. And another feature about this reaction is, notice this equilibrium sign, right? Yeah. Both pairs of acids and bases are typically in equilibrium with one another, unless and until one of them is extremely strong, the equilibrium does not proceed to any particular side, right? This is our understanding of acids and bases at a broad level as happening on Earth. Now, if you consider a reaction happening in space, okay? Consider a similar acid-base reaction happening in space. What is the reaction I'm talking about? Take, for example, H2 plus H2 giving rise to H3 plus H. Now, H2 here in this reaction is acting as a base and H2 plus is the acid. So H2 abstracts the proton from H2 plus to form H3 plus and from H2 plus, because the proton is gone, you have the H here. Now, of course, note that I haven't told you how this reaction is happening and why this reaction is happening in space. However, for now, take it for granted. As the course proceeds further, I shall precisely explain how and why this reaction happens. Okay, right? Now, notice the first point. The first point to note is that in the interstellar medium, as we study acid-base chemistry on Earth, right, we have a solvent. Note, no solvent in majority of space. Okay, there's a reason why I've used the word majority here. I've not said all of space, but only majority of space. There's a reason for that. I'll come back to that in the later parts of this lecture. So this is one first difference. The next difference is that, see, on Earth, what do you call a base? A base is something which is typically containing an electronegative atom with lone pairs of electron. But here, what is acting as the base? It is the hydrogen itself, correct? Right? So, molecules show unexpected reactivity pattern. For example, if you say H2 to be a base on Earth, you will be laughed at, right? And your teacher will most likely not even give you the marks. Okay, molecules show unexpected reactivity in space. And notice the third feature. Over here, I have given an equilibrium sign. That is, unless and until we have an extremely strong acid or a strong base in this side or on the other side, right? We typically encounter an equilibrium scenario here. However, on space, right, reactions most typically are unidirectional. So look at how much difference there is between, acid-base chemistry happening on Earth versus acid-base chemistry happening on space, right? So once again, this example highlights that we have so much more to learn, right, about the molecules in space and what they teach us about enhancing our knowledge of chemistry itself. Okay, right? So far in this lecture, I introduced you to the idea of what astrochemistry is and said that astrochemistry could connect astrophysics with astrobiology because the place where life is formed, that is studied in astrophysics, and how life itself is formed in the universe is studied in astrobiology. Now, molecules is a common connecting factor. After that, using the example of two reactions, one a redox reaction and another acid-base reaction, I illustrated to you how there are different types of chemistries to be understood in space and how they augment our knowledge of chemistry on Earth. Okay, on that note, I'll meet you in the next lecture. Thank you.